One start.
Hello, we are going to present our work on quantum random number generator. Myself, Soumyajyoti Datta, and here are my teammates, Mausumi Kundu and Chitra Rai Chaudhary. So at first, we are going to discuss what do you mean by random. So if we look at the dictionary, random roughly means unpredictable. So when it comes to unpredictability, we can think of only probabilities. For example, let's consider a spinning coin or when we are flipping a coin. So while it's spinning, it's state of both superposition, head and tails. I mean, it's superposition of both head and tail, as we see or observe in daily life. See, we will not be able to predict the results until the coin is collapsed into the ground. Okay. And now if we denote head as 0 and tail as 1, and we perform this random experiment in n number of times, we will get a random bit string of 0 and 1 of length n. Okay. So these random numbers are very much essential in cryptography, Monte Carlo numerical simulations, lottery, statistical research, randomized algorithms, and even in gambling. But there is a catch. We think the spinning coins and the results are very much random, but they are not much as random as we think, because we don't know anything about the spinning coins, so our knowledge is incomplete. And in classical world there are some hidden variables, like the mass of the coin, its shape, the amount of force required to spin the coin, air resistance. We don't know these things, but we can know these things. So, and when we know these things, we will be able to determine or predict what outcome would really be after spinning the coin. So we can construct some function to calculate all this information, and then we will be able to easily predict the resultant bit string successfully.
So, how Shomojyoti discussed that the probabilistic thing will collapse into deterministic thing. Same thing is happening in the random number generating algorithms, whatever we use nowadays. When we ask the computer to generate a random number, the computer uses a variety of information to calculate it and also generate a random bit string. These parameters, such as current data in, value of pi, information about the user, and so on, these are the parameters. These types of random number generators are called pseudo-random number generator, or is simply PSRN, or deterministic random bit generator. That pseudo-random number, that means from its name that it is looks like a random, but it is not actually random. So if we know the parameters used and how they are used to generate the random bit sequence, we will be able to determine the numbers easily. That means that when we have knowledge about the parameters, the thing will collapse into deterministic world. This is a weak point or a drawback of current random number generating system that can be used by hackers to break encryptions.
To counteract this, we have a principle in quantum mechanics called the superposition principle, where the particle can be in its every possible state simultaneously, but collapse to a single state or a particle state when observed or measured. We all know about the electron double slit experiment, where we conclude that a light exists in the superposed state of both wave and particle, not in any particular but when it is subjected to measurement or any perturbation is given to the initial system, it is found to be in its uh, particle state or the wave state, that is one specific state. Now, unlike spinning coins, it is totally unpredictable. There is no hidden variable by which we can predict the outcome of the measurement. So we can take the advantage of the quantum world to build a true random bit sequence generator.
So there are many ways, or we can say more than one ways to create the quantum random number generator. So we can construct them using Hadamard gate, but we can also use Bell states and quantum walk to create QRNG. But here we are demonstrating the simplest one. I mean, where we have used the Hadamard gates only. So at the first code block, we have imported the necessary libraries like Qiskit, Qiskitair, and all those things. And as we are running the circuit on Quasum simulators, we have also imported Quasum simulator. After that, we have taken the length of the bit string as input in, and we have passed the bit string into the as a parameter of the quantum circuit. Then we applied for loop, and we have drawn the circuit for the bit string of length 5. After that, we have run the circuit on the Quasum simulator for one shot to get the random number, and I mean we have obtained the random bit string. Then we have converted it to the decimal, and we have got the random number 9 here. After that, to demonstrate the superposition principle, we have run the circuits multiple shots for 1000. Here we have for 1024 shots, and then we have observed the result and we have plotted them into histogram for better understanding.
From the plot, we can see that some numbers are returned more often than others. This is because of the fact of intrinsic noise in the quantum system. In this case, we use quantum simulator. The phenomena where certain values are returned more frequently than others during quantum measurements can primarily be attributed to intrinsic noise in quantum systems, which arises from several factors like imperfect gates. Quantum gates do not always perform perfectly. For this, noise can arise. Also, measurement errors. The process of measuring qubits can also introduce additional errors, where the expected outcomes do not match the actual measurements due to readout noise.
There occur state preparation errors. That is, if the initial state of the qubits is not prepared accurately, it may not be in a proper superposition. This could cause certain measurement outcomes to appear more frequently. Qubits have a limited time, that is, we can say it is a coherence time, which is to maintain their quantum state before decoherence occurs. If the operations are performed too slowly, the state may collapse before the measurement, leading to biased result.
So here we can see the errors mainly occurs due to the relaxation time. I mean the time in which the qubit eventually returns to its ground state, and it's when we are taking much longer time to measure the circuits. So to counteract this or mitigate these errors, there are several error mitigation techniques like readout error mitigation, zero noise extrapolation, gate twirling, and probabilistic error calculation cancellation. Besides that, there are some like dynamic decoupling, error aware compilation, etc. But in our code, we have used readout error mitigation, zero noise extrapolation, and gate twirling, and we have compared them with the circuit where no mitigation error is applied to view the accuracy. Or okay, so for this, we have used a quantum computer of 127 qubits, IBM Brisbane, as our backend. Then at here as a operator for which we are going to measure the expectation value. So we have used Pauli X operators or Sigma X operator. Then we have constructed some we have transpiled the circuit. I mean, we have broken into, I mean, decomposed in the gates, Hadamard gate into some fundamental gates. Okay. And after that, we have mapped the problem into the 127 qubit device. Then we have used estimated and those and those things and run those mitigation results. I mean, as a batch. So here our quantum system only takes on can only three jobs at a batch. So at we have divided the job into two batches. One first batch we have used no error mitigation, gate twirling, and zero noise extrapolation, and the second batch we have used error mitigation in the place of zero noise extrapolation. So from the first result, if we look at the histogram, we will see there is no significant improve over the no mitigation state, and the zero noise extrapolation is showing even less expectation value than our no mitigation state. So next we move to the second job batch. So here, after performing the no error mitigation, read or mitigation get twirling, we get the follow up and plotting the result, we get the following. So surprisingly here, to twirling is showing 100% expectation value, and readout error mitigation also showing 100% expectation value, so which is quite significant improvement in from before. And so this results highlights the importance of error mitigation techniques in quantum computers, especially in noise intermediate scale quantum devices, and where noise plays a critical role in degrading the quality of results. So these are the real devices, and there will always be noise. We can always minimize the noise, but there will always be this techniques using which we can mitigate the noise, and using a near perfect quantum random numbers generator. So thank you for all your attentions.
That's
That's all.